and to focus on this method presented at the end of the chapter called conceptual analysis, where you're presented with the three different kinds of conditions and you have to reason through in order to answer the question, which is why you're doing the conceptual analysis in the first place. So let's just remind ourselves that we're not so much in logic or in philosophy generally interested in sentences as in what is being asserted in the sentences that people make. So the thing is, declarative sentences are what we use when we're trying to say something or assume something about the way the world was, the way the world is, or the way the world will be. And the virtue of declarative sentences is that they have this property of being either true or false. We typically think of statements as what a declarative sentence asserts or means, but it isn't itself a declarative sentence. The virtue of talking about statements is we can focus on what a sentence asserts and not be worried about where the period is. Because it turns out you can express an argument in the form of a single sentence, and what matters for us is recognizing arguments, the reasons that are being given and for the claims we make, not looking at the period. So for us, as in every logic class or every philosophy class, it's what's being asserted that matters. And what's going to be asserted will be a sentence in English, but it's the statement that's being asserted that's going to matter to us. And statements, again, like declarative sentences, have this property of being either true or false. They have a truth value. Now, of all of the things in the universe, and some of you have had me before, so you should know what the answer to this question is. Of all of the things in the universe, of every object in the universe, what are the only kinds of things in the universe that have the property of being true or false? That is, have this property of having a truth value. I've just identified two of them, so it's not so complicated.
Declarative statements.
Declarative sentences, what did you say?
I said declarative statements.
All right. Declarative sentences have the property of having a truth value. They're either true or false. What else? It's not a trick question. You got to apply it. What else has the... I just told you. You got a whole table here full of them. What else has the property of being either true or false? Statements. What else? Kittens. Houses. Vanilla Stoli Black Russians. Pork chops, chairs, tables, cars, motorcycles, boats, oceans, water, rivers. Anything else? Does anything else in the universe have the property of being either true or false?
What about beliefs?
What?
Beliefs?
Yeah, I think that's the only other thing. Assuming that beliefs exist, we typically talk about beliefs being either true or false. And in fact, in the context of philosophy, we say in the traditional conceptual analysis of the concept of knowledge, which is one reason why we use conceptual analyses, something we'll be talking about later today. Three conditions must be met in order for you to know something. You need to believe it, you need to be justified in believing it, and it needs to be true. Well, that can't happen unless beliefs can be true. So the point is, of everything in the universe, only three kinds of things have the property of having a truth value. Declarative sentences, statements, which are what declarative sentences assert or mean, and beliefs. That's it. Not kittens, not rivers, not people, not chairs, not houses, and all the unlimited number of other things in the universe. Yes?
Put in the form of a statement or declaration?
No, I think that for the folks that believe in beliefs, that they think that beliefs exist, that it's possible to have a belief even when it isn't expressed linguistically.
But is it possible to have a belief unexpressed have a truth value?
Yeah. We're going to run into some murky ontological ground here because then, well, where is this thing that has this property if it doesn't exist, right? Which is why lots of folks are quite comfortable, like Quine, for instance, with eliminating belief talk altogether because belief talk doesn't really contribute much to our understanding of certain things. But I'm just saying, all right, lots of people think that beliefs exist. We have it in the traditional concept of knowledge, so I'm not trying to settle that particular ontological question because there are some interesting ones. In any event, what this table captures are all the different kinds of statements that there are. And statements, again, are what declarative sentences assert or mean. Notice that some statements are statements that have no other statement as a component. And we call these statements atomic statements. For instance, Sophie is a cat is an atomic statement. It's got components, it's got a logical structure, it's got a name, and we're asserting exactly one thing about her, namely that she's a cat, but it doesn't have another statement as a component. Identity statements. Bruce Wayne is Batman, for instance. has a logical structure. It's got a name, it's got another name, and the whole thing will be true just in case the two names refer to the same individual. But it has no other statement as a component. And the same goes for general statements. And let's take a look at like a statement of this form. All S is P. Now, we call these four types of statements you see here standard general statements because they consist of exactly one quantifier, which is that word or phrase that indicates how many members of the class are being referred to. And the thing about general statements is, without exception, a general statement is always about all or some of the members of a class of individuals. If we're about a specific named individual, it wouldn't be a general statement. So general statements, it turns out, are very useful for us in a variety of contexts, especially in science, when we want to make a true generalization over a range of objects in a particular domain, instead of having to make a long conjunction of every single object in a domain. For instance, think about it like this. If I wanted to say something truly about every person in this class, I could do so in an inelegant way by saying, Rob is a person in this class, and Rob is over 21. And Joshua is a person in this class, and Joshua is over 21. And Ann and Carl, yada, yada, yada. For each and every one of you, I end up with this long, big conjunction. Instead of, more elegantly, everyone in this classroom is over 21, which I hope is true. Right? Notice the difference there. I can make, in a very simple and elegant way, an assertion that applies to each and every one of you, without naming each of you individually. And that's a general statement. It applies to the class of individuals. That is all the individuals in this class. Give me another property that's true of everyone in this class. Every person in this class is what? That is, all people in this classroom are alive individuals. All people in this classroom are... Is that true?
Wait, we're students at the University of Utah. Or no, I guess...
Am I people?
He's not a student of this class. So that wouldn't actually be true.
The who?
I'm a student.
Well, yeah, you are. Yeah, you're a general student.
Give me something that's true. All people in this class are human. All people in this class are wearing true.
We had that one guy that last semester didn't wear shoes.
Well, then it wouldn't have been true. If I'd uttered it then, it'd be false, but now it's true. The point is, that's a more elegant way of saying something than my having to say the long conjunction that applies to each and every one of you. Does that make sense? Either get it or you don't. You get that universal statements are never about specific named individuals. Even though in order for the statement to be true, sure, in most cases it'll be true about specific named individuals, but the general statement itself is never true or false because of any specific named individual. It's about what it asserts about a class of individuals. General statements are always about a class of individuals. That's what makes them general statements. General statements, without exception, no matter how complex their structure, are always atomic statements. So, for instance, all S is P, no S is P, some S is P, some S is not P. These are the forms of standard general statements. Standard general statements consist of exactly one quantifier, exactly two terms, and some form of the verb to be. That's what makes them standard. If you've got more than one quantifier, or more than two terms, then you don't have a standard general statement. It ends up being a complex one. A complex general statement is simply any general statement that's neither simple nor standard. Well, it turns out that many of the kinds of statements that we're concerned with when we do or use conceptual analysis are complex general statements. Many of the statements that qualify as laws in science are complex general statements. So you need to have some understanding of what the hell complex general statements are. That's what I'm talking about. So we're going to talk about that today and the difference between complex general statements and conditionals in particular. So I've talked about the difference between atomic statements and compound statements. If a statement does have another statement as a component, well, it's a compound statement. There are two kinds of them. And it's the connective that determines what kind of compound statement it is. If the connective conjoins statements into a type of statement where the only thing you need to know to determine the truth value are the truth values of the components and the rule for computing the truth value, then it's called a truth functional compound statement. If the connective is such that it's conjoining statements into a larger statement where you'll always need to know something else besides the truth values of the components to determine whether it's true or false, then that's non-truth functional. So let's begin by taking a look at those, and we'll revisit the general statement bit. All right, so There are different kinds of compound statements, as you know. In order for a statement to be a compound statement, it must have at least one other statement as a component. And what makes it possible for us to conjoin statements into larger compound statements are what are called connectives. So a connective will be a word, phrase, or even a symbol that allows us to conjoin statements into larger statements. So consider these two rather innocuous statements. One's a singular atomic statement, and the other is a general statement. Lieutenant Commander Data is a machine, and some machines can think. Well, there are an unlimited number of ways I can conjoin those two statements into a compound statement. I can use "it is false that" to deny that some machines can think. And that resulting larger statement is called a negation. That's a truth functional compound statement. Lieutenant Commander Data is not a machine. That's the denial of Lieutenant Commander Data is a machine. Lieutenant Commander Data is not a machine, but some machines can think. That larger statement is a conjunction. The main connective is the but that determines that it's a conjunction. Either Lieutenant Commander Data is a machine or Lieutenant Commander Data is not a machine is a disjunction. How do I know that? Through the connective or. If Lieutenant Commander Data is a machine, then some machines can think. Some machines can think if and only if Lieutenant Commander Data is a machine. I'm not just going to read through the examples. The point is all I'm doing is using not, it is false that, and, or, if, then, if, and only if to conjoin statements. Any two statements can be conjoined with and the result is a conjunction. Any two statements can be conjoined with or. The result is disjunction. Any two statements can be conjoined with if, then. The result's a conditional. Any two statements can be conjoined with if and only if. The result's going to be a biconditional. It won't always be reasonable, but it'll be a statement of that type. Yes?
Yeah, Lieutenant Commander Data is not a machine, but some machines think. That makes good sense to me for compound. But Lieutenant Commander Data is not a machine.
Where are you? You mean
Same page.
that is, all right, well, think of the statement. The first statement is just see at the top here.
Yeah.
Lieutenant Commander Data is a machine.
Right.
Right? That's a statement. Any statement in the universe can be denied. All you have to do is put "it is false that" in front of it. And another way of doing that is putting "not" within the statement. So another way of denying that Lieutenant Commander Data is a machine is to say "it is false that Lieutenant Commander Data is a machine." Another way of doing it is to say Lieutenant Commander Data is not a machine. Those two sentences mean the same thing.
Okay.
Every statement in the universe, just to repeat something I did talk about last class. This is a variable. This is a small p. We use variables in logic, p, q, r, s, t, and so on, in the same way that we use variables in mathematics. Whereas variables in mathematics are placeholders for numbers or mathematical or arithmetical expressions, variables in logic are placeholders, or in this case, these variables are placeholders for statements. So every statement is a substitution instance of a statement form. So the most basic statement form is this one, p. Every statement is a substitution instance of this statement form. Any statement can be denied. How do I do that? Put "it is false that" in front of it. And symbolically, we have a symbol that allows us to do that. And that's this little squiggly symbol. It's called a tilde. So what this is the form of every negation in the universe. It wouldn't be a negation unless there were a statement and its denial. That's what makes it a negation. Any two statements in the universe can be conjoined with "and." That's a little off-center, but and the result is the form of a conjunction. Sophie is a cat. God exists. Sophie's a cat and God exists. Poof, that's a conjunction. Sophie is a cat or God exists. This is the form of a disjunction. Any two statements can be conjoined with "or." Any two statements, and I'll focus on this one, can be conjoined with "if then." The result is a conditional. Sophie's a cat, God exists. If Sophie's a cat, then God exists would be a substitution instance of this. Finally, Sophie's a cat, God exists. Sophie's a cat if and only if God exists is what we're expressing here. So the point is, statements are substitution instances of statement forms. Every statement's a substitution of this one. And in order to deny a statement, all you got to do is say "it is false that" in front of it. But what we're illustrating here in this table is that there are all kinds, an unlimited number of ways of conjoining statements using connectives. There are two flavors of connectives. Truth functional ones, the ones that result in statements that are negations, conjunctions, conditionals, biconditionals. I think I got them all. Negations, conjunctions, disjunctions, conditionals, and biconditionals. The other kind of connective is a non-truth functional connective, like the ones you see down here. That is, believes that, fears that, knows that's a special case, because, for example. So let's talk about these connectives for a second. The reason why because is not a truth functional connective like it is false that, and, or, if then, and so on, is because, take a look at the example. Andy failed his course because he did not take the final. Clearly this is a compound statement. Why? Because it's a statement that has another statement as a component. In fact, what are the two components? Andy failed his course is one of them. Andy did not take the final is another one. But the reason why because is a non-truth functional compound connective is because it turns out that in order for the larger statement to be true, the reason why Andy failed must be because he didn't take the final. That is, knowing the truth value of the two components isn't good enough, isn't sufficient for you to determine what the truth value of the whole thing is. And that's the case in every single non-truth functional connective. So I went through this example last class. Notice that in each of the cases down here, Abraham Lincoln was born in Illinois is the statement, is the component statement. But in each of these cases, we've got a different propositional attitude that's being expressed about it. Pat believes that Abraham Lincoln was born in Illinois. Pat hopes that. Pat desires that. Pat fears that. Pat hates that, whatever. In each of those cases, it turns out the truth value of Abraham Lincoln was born in Illinois is irrelevant to the truth value of the whole thing. What matters in the case of Pat believing it is it will be true just in case Pat believes it. The truth value of the component is irrelevant. That's why it's non-truth functional. You've got to know something else besides the truth value of the component, and so on. So does that make sense? All right. Because is a connective, but it's not a connective like and or, if then, and so on. So of those connectives, the kind of connective that really matters to us, given the stuff that we're going to be talking about, is the connective that we use in order to express conditionals. And take a look at the list here. There are lots and lots of ways of expressing conditionals in English. Typically, it's if-then, right? But just because a sentence has if-then in it doesn't mean automatically it's a conditional, for reasons that you'll see when we get to the end of the chapter here. But notice that if P, then Q. If P, Q. P only if Q. Assuming that P, it follows that Q. Given that P, then Q. Granted that P. In case P, then Q, and so on and so on. And each of those forms of statements, the P is on the left, the Q is on the right. Look at the second column. Q if P, Q when P, Q so long as P, Q provided that P, and so on. In each of those expressions, the Q is on the left and the P is on the right. And here's why this matters. There are 5 kinds of truth functional compound statements. The first kind, which we've just been talking about, are negations. Negations have this form, tilde P. The second kind are conjunctions. Conjunctions have this form. The dot here is taking the place of and. Any two statements can be conjoined with and the result is a conjunction. In order for a conjunction to be true, both conjuncts, that is, the components, have to be true. The second, or the next kind, is a disjunction. Any two statements can be conjoined with or, and the result is what's called a disjunction. In order for a disjunction to be true, at least one of the two components has to be true. But now we're talking about a statement of this form, P hook Q. And here, it's not the order of the components as they occur in the sentence that matters. It's what's following the if, or what's functioning as the if in the sentence. So if we go to the text, we see that P in every single one of these expressions, with one exception, that is the only if, that P always follows the if, or what's functioning as the if. And there are lots of ways of expressing the if. So you can say if, provided that, assuming that, on the condition that, and so on. So here's what matters. The parts of a conjunction, which you see here, are called conjuncts. Any two statements can be conjoined with and. The parts of a disjunction are called disjuncts. Any two statements can be conjoined with or. The parts of a conditional are not called conditional uncs. They're called the antecedent and the consequent. The antecedent is that part of a conditional that, if true, should allow for something else to occur. It's the conditional relation in a conditional statement. So the antecedent is what follows the if. The consequent is what follows the then. So if this happens, then this ought to happen. That's what the whole conditional statement's asserting. So it's crucial that you pick out what the antecedent and what the consequent is. And as you can see from the list here on the right column, the antecedent isn't always listed first. So you can't always go on the order of the words in the sentence. What matters is what's following the if, or what's function is the if. That will be the antecedent. And when you write the conditional, it needs to be written in this order. So there is no one symbol that takes the place of if-then. But when we write a conditional, the antecedent is always to the left of this little hook. That's how you know what the antecedent is. There's never any ambiguity. The consequent is always written to the right of the hook symbol. That's how you know what the consequent is. So you go from the English order in order ultimately to write the sentence in the proper form. This is the form of a conditional. All right, you're with me here so far? Now, the thing about conditionals is, and I'm emphasizing this because it matters, generally speaking, and that is with one exception, the antecedent of a conditional is going to be that which follows the if, or what's function is the if. The only exception to that is when the connective is only if. When the connective is only if, the antecedent's before it. But in every other case, the antecedent's going to be after the if. The reason why this matters is that when you have if in the middle, as you do here, you're expressing what's called, as you'll see here, I'm going to get to this in a couple minutes, a sufficient condition. A sufficient condition captures what's good enough. So in this case, Q if P, P's a sufficient condition. It's not necessary, but it's good enough. That's all that's required. That'll do. But when you have, in this case, only if in the middle, you're expressing something that's necessary, something that must be the case. P in the middle and only if in the middle are not interchangeable. They mean different things. They have different roles. And when we get to, as we'll see here in a second, if and only if, well, that's expressing something even stronger. In any event, let me get to the rule here. The rule for computing the truth value of a conditional, we can put this way, that every substitution instance of this statement form here, that is if P then Q, that is if P then Q, will be false when and only when, if and only if, just in case, those are different ways of saying the same thing, the antecedent's true and the consequence false. Now think about that. If you can't pick out what the antecedent and the consequent are correctly, then you won't be able to determine whether the damn thing's true or false. It's easy to determine whether a conjunction is true. In order for a conjunction to be true, each conjunct has to be true. In order for a disjunction to be true, at least one disjunct has to be true. But in order for a conditional to be true, what can't happen is for that to be true and for that to be false. So take a look at an example here in the text. If your head is severed from your body, then you are dead. Expresses something that's true. And notice that the antecedent's false and the consequence false. And the antecedent's false because your head is not severed from your body. The consequence is false because you're not dead. But do you really have a problem with saying that this conditional statement is true? Probably not. In the same way that, and I used this example last class, if you walked into a store and someone said, if you steal that, I will prosecute you, is true even when you haven't stolen anything and you haven't been prosecuted. The point is, and this is an odd kind of case I get, but I think you can understand it if you think about it. Conditional statements can be true even when both the parts are false. In fact, conditional statements with a false antecedent are true, regardless of what the truth value of the consequent is. The only way of making a conditional false is when the antecedent's true and the consequence false. Because what that conditional statement is asserting is then when this is the case, then this ought to happen. So when this is the case and that doesn't happen, what the larger conditional is asserting is false. But that's the only way of making a conditional false. So this example here, if Homer Simpson is now president of the U.S., then no pig can fly, is true. That doesn't make it reasonable, however. So we'll touch on that next week. Just because any two statements can be conjoined with if-then doesn't mean it's going to be a good reason or good evidence within an argument. Sophie's a cat, God exists. If Sophie's a cat, then God exists. If God exists, then Sophie's a cat. Well, when you're concerned with whether it's true or false, the only thing that matters are the truth values of the antecedent and the consequent. When you're concerned with whether that's reasonable evidence as a part of an argument, well, we've got to consider the causal relation and what possible causal relation exists between those two things. Okay, we'll get to that, right? But when the issue is whether it's true or false, you need to accept that a conditional is false only on one possible combination, namely when the antecedent is true and the consequence false. Otherwise, it's true. The final kind of truth functional compound statement has this form, P if and only if Q. We use this 3-bar symbol to capture that. And notice that this 3-bar symbol looks a little bit like that symbol. How do we use this symbol? It's the symbol for identity, for equality. And the 3-bar symbol looks a little similar to that. And the reason for that is what biconditionals do is assert a kind of identity. But it's not an identity of meaning or of reference. Rather, it's an identity of truth value. So what makes a biconditional true, as you'll see, is when both bijuncs agree in truth value. If they're both true, then the whole thing's true. If they're both false, the whole thing's true. Let's summarize this here in another slightly different way. So for a conjunction, in order for a conjunction to be true, both conjuncts have to be true, right? So if P is true and Q is true, the whole thing is true. Otherwise, it's false. So if P is true and Q is false, the whole thing's false. True, false is false. True, false, false, and false is false. For a disjunction, P, wedge Q, there are 4 possibilities. True, false, true, false, true, true, false, false. The rule for a disjunction says that in order for a disjunction to be true, at least one of the disjuncts is true. So when they're both true, the whole thing's true. When one's true and the other's false, the whole thing's true. When one's true and the other's false, the whole thing's true. The only way of making a disjunction false is when they're both false. For a conditional, if P, then Q. Again, 4 possibilities. True, false, true, false, true, true, false, false. What the rule says is that the only way of making a conditional false is when the antecedent's true and the consequence false. Otherwise, when the antecedent's true and the consequence true, the whole thing's true. When the antecedent's false and the consequence true, the whole thing's true. When the antecedent's false and the consequence false, the whole thing's true. What we're talking about now are biconditionals. Again, 4 possibilities. True, false, true, false, true, true, false, false. Again, this symbol captures a kind of identity, but not an identity of meaning or of reference, an identity of truth value. So when the bijuncs agree in truth value, the whole thing's true. They agree when they're both true, they agree when they're both false. But when one's true and the other's false, then there's not that identity of truth value, so it's going to be false, false. Notice that this column, this column, this column, and this column are all different columns. Why? They're different kinds of truth functional compound statements. You'd expect that. So they're not interchangeable. We can't use and or if then, and if and only if interchangeably, because when we do, we fundamentally alter what type of statement's being asserted. There are 5 kinds of truth functional compound statements. The 5th being, of course, this one, tilde P. There are only 2 possibilities. When P is true and when P is false. When P is true, the denial of P is false. When P is false, the denial of P is true, because the rule says any negation or substitution instance of this statement form is true when and only when, if and only if, the statement being denied is false. This summary here captures the 5 kinds of truth functional compound statements and the conditions that must be met in order for them to be true or false. Now, biconditionals, again, are a kind of truth functional compound statement. And a truth functional compound statement with if and only if, or what's equivalent to it, just in case, when, only when, is a truth functional compound statement. But not every sentence that has if and only if in it is a biconditional. Not every sentence that has if then in it is a conditional. And that's one of the take-home messages for today. So let's shift our attention here to conceptual analysis, which is a method for reasoning well at the level of a single statement. And basically what you do with a conceptual analysis is you've got a concept, some idea, some notion, whatever, that you want to analyze into all of its necessary parts. And when you've analyzed it into all of its necessary parts, then together they're jointly sufficient, good enough. That's what a conceptual analysis is. You're going to see several examples of this. But in the end, conceptual analyses are going to require that you construct a sentence that's one of 2 things: a biconditional or a complex general statement. It's got if and only if in it. Because we're going to use both truth functional compound statements and general statements to express sufficient conditions, necessary conditions, and necessary and sufficient conditions. All right, so let's turn our attention to the 3 kinds of conditions. So generally speaking, a condition is something that causes something to happen or for it to be true. And this is a class in the philosophy of science. So ultimately, we're going to be concerned with causes of things, identifying the causes of things in order to provide explanations for why things are that way. That's one of the main jobs of science, to explain to us why the world was the way it was, why it is the way it is, and how it's going to be in the future. Explanation versus a prediction depends on whether the event that you're trying to explain has occurred or not. You're going to learn the logic of this. But you can't provide explanations for why things happen without there being some kind of causal relation between the thing that happened and the thing that caused it. So we'll be talking about this stuff over the course of the semester. Now, there are three kinds of conditions. The weakest kind of condition is called a sufficient condition. And whenever you hear the word sufficient, the word that ought to automatically pop in your mind is, well, good enough. That's all a sufficient condition is. So when someone says that's sufficient, that doesn't mean, man, it's necessary. It doesn't mean it's required. It just means it's good enough. So what a sufficient condition expresses is not something that has to be the case for something else to occur, but it's good enough. So a sufficient condition Q for any given effect or belief P can be expressed as a conditional statement of this form, P if Q. And in that form, what's the antecedent and what's the consequent? Look at P if Q is a sentence that expresses a conditional. How do we write that conditional in the form of the conditional? Let me write that down. P if Q. What's the antecedent of the conditional that's being asserted here? And how do you know it's Q? Because what?
Follows if.
Right, because the rule is that the antecedent is going to be what follows if, or what's function as a if, with the only exception of the connective only if. So since Q is following the if, how would we write this in the form of a conditional? Not the arrow, but Q hook P. Because in my system, at least, we use the hook and not the arrow. In some systems, they use an arrow to take the place of what I use for the hook. Does that make sense? Are you with me here? So let's ignore that for a second and notice that when we go from this way of expressing something with if in the middle, the result is a conditional statement whose antecedent is Q. So the antecedent isn't always P. It's just that when we write the form of a conditional, as when we were talking about it before, like right here, when we write the form of a conditional, we typically always begin with P because it's the first variable. Then we go to Q. But that doesn't mean P is always the antecedent or Q is always the consequent. Rather, it's their position within the sentence. So here, if I were to express a sentence of this form, P if Q, well, Q is going to be the antecedent. Why? Because it's following the if. All right. Notice that the only way of making it explicit, in fact, that you're expressing a sufficient condition is if you put if in the middle. Because if I were to write if P then Q, how about Q if P? Focus on what I have here in these two. If, shit, that's messy, sorry about that. If P then Q versus Q if P. The only one of these two expressions that makes it clear that I'm expressing a sufficient condition is when if is in the middle. Because I can always translate something with if in the middle into the form of a conditional. But when it's in this form, I can't tell whether it's a sufficient condition that was expressed or a necessary one. So the only way of making that explicit is when you put if in the middle. So if you want to make it explicit and you're using a conditional statement, then you put if in the middle. But notice that there's a difference here between the sufficient conditions expressed here versus the sufficient conditions that are expressed here. These are conditional statements. Conditional statements are truth functional compound statements. These are general statements. Just because a sentence has if in the middle doesn't mean that it's a conditional. So we're concerned with picking out not just what kind of statement's being asserted, in this case, what kind of condition is being asserted. So take a look at the first examples here. Fido is a mammal if Fido's a dog. Now think about that. Granted, as it applies to Fido, Fido can't be a feline or, it can't be both a dog and a feline. You can't be, a whale. The idea is that, is it necessary that in order for something to be a mammal that it be a dog? No, it's good enough. It's sufficient. That's the idea. Brandy is a doctor if she has a PhD. That is, having a PhD is good enough in order to be a doctor. Is it necessary that you have a PhD in order to be a doctor? Did I say that right? Yeah. Is it necessary?
No, you can be an MD.
That is there some other way in which you can get a degree and still be a doctor? Yes, you can be an MD. You can have a doctor of dentistry or whatever it's called. You can have a doctor of veterinary medicine and be a doctor. Point is, it's sufficient. It's not necessary, it's good enough. Take a look at the examples at the bottom. Something is a mammal if it's a dog. Expresses something that's sufficient, not something that's necessary. Anyone is a doctor if she has a PhD. Any truck is low on fuel if its gas indicator light is illuminated. Pay attention to this. Just because a sentence has if in the middle, which means it's expressing a sufficient condition, doesn't mean that it's expressing a conditional. Why? Because those bottom three examples are general statements that have if in it. You can't tell that a statement's a conditional just because it's got an if in it. You have to analyze what's actually being asserted. If it's being asserted about a specific individual, as this case of, say, Brandy is a doctor, if she has a PhD, well, that's a truth functional compound statement that consists of two components. Brandy is a doctor, Brandy has a PhD. Whereas anyone is a doctor if she has a PhD, that she is referring to anyone. You can't treat anyone as a doctor as a component, and she has a PhD as a component because that she's referring to the anyone. You got to pay attention to that. In any event, I say here that the presence of if alone doesn't determine that that sentence is expressing a conditional any more than a smile indicates that someone's happy. The point is, again, we're concerned now with identifying the different kinds of conditions, recognizing what kind of conditions being asserted. We're not really concerned with evaluating the reasonableness of a sufficient condition, because any two statements can be conjoined with if, and the result's going to be a sufficient condition. Like, you are a student if you're a cat, is a sentence that expresses a sufficient condition. In fact, it's a sentence that expresses a conditional. In fact, a conditional that happens to be true. That doesn't mean that it's reasonable. However, that's a separate issue than whether it's true or false, or what kind of condition is being asserted. Do you understand that? Okay. So we'll deal with it. Just can't deal with it now. The second kind of condition is called a necessary condition. Whereas a sufficient condition is good enough, a necessary condition captures something that must be the case in order for a certain event to occur, for a certain belief to be true. This is much, much stronger than a sufficient condition. And notice that the connective that we need in order to capture a necessary condition is the connective only if. When if is in the middle, and I'll do it in this order, P if Q, I'm expressing a sufficient condition. And what's the antecedent of the conditional that's being asserted here?
Q.
Q. When I say P only if Q, what's the antecedent of the conditional that's being expressed here? Q. Is it?
If.
Oh, sure, you listen to me wax on about this stuff. Oh, yeah, it makes sense. But I'm asking you to apply it. What's the antecedent of the conditional that's asserted in that second?
P.
Why is it P?
Because you've got only if.
That is, the rule that you're following in order to pick out what the antecedent is this, that the antecedent will be what's following the if with one exception, when the connective is only if. So if you were to translate what this says symbolically, you would do so this way. If Q, then P. If you were to translate what this says symbolically, you would translate it this way. If P, then Q. These are not the same thing. So, this only if connective captures a necessary condition, something that must be the case in order for a certain effect to occur, for a certain event to be true, for a certain belief to be true. Something that's necessary. And this is a metaphysical concept. So how's about some examples? You will pass my course only if you attend class. Expresses something that's necessary, not something that's sufficient. It's just something that's necessary. Buffy is a resident of Florida only if she lives in Florida. Our plane will reach its destination only if it carries enough fuel. Each of those sentences asserts a conditional whose antecedent is to the left of only if. Why? Because that's the rule. The antecedent is going to be what follows the if unless the connective is only if. But what you have in those bottom three sentences there, each beginning with a quantifier, is a general statement that has the connective only if. So we can use general statements to express not just sufficient conditions, but necessary conditions. In this case, something has a mind only if it is rational. That it is referring to that something. You can't take something has a mind as a component and it is rational as a component because that it's referring to the something. You need the whole thing. That's why it's an atomic statement. Someone is a medical doctor only if she has an MD. Is expressing something that's necessary. That is, it's a general statement. It's not about Buffy or a specific named individual. But general statements always, without exception, are atomic statements. Someone is a doctor of philosophy only if he has a PhD. That's expressing something that's necessary. Why? Because of the connective only if. They're not interchangeable. All right, does that much make sense? Okay, then. Again, just as any two statements can be conjoined with if, any two statements can be conjoined with only if, and the result's going to be a necessary condition. That doesn't mean it's going to be reasonable. Sophie's a cat. God exists. Sophie's a cat only if God exists. Sophie's a cat only if the moon is not made of green cheese. Sophie's a cat only if Rob is wearing a hat. They're all expressing necessary conditions. I'm not saying they're all reasonable. Because what possible relation exists between Sophie being a cat and my wearing a hat? Right? That's dubious. There's a dubious assumption there. But when the issue is what kind of condition, it doesn't matter whether it's reasonable. When the issue is it true, it doesn't matter whether it's reasonable. When the issue is, when we're evaluating the evidence, is it reasonable? Then we can tackle that. You'll learn some specific things to say. The final kind of condition, the strongest kind of condition, is what's called a necessary and sufficient condition. So, symbolically, I'll do this. P, if and only if, not leaving myself a lot of space. If we were to translate this, the result would be a straightforward biconditional statement. Any two statements can be conjoined with if and only if. And we use if and only if in order to express necessary and sufficient conditions. When we do so in a truth-functional compound statement, the result is one of the 5 kinds of truth-functional compound statements, namely a biconditional. But we can also use if and only if in a general statement. So here are some examples. You will pass this course if and only if you attend class. Is not true, right? Because what's being asserted here is that it's necessary, and it's the only thing that's necessary, and that ain't true. Brandy will get an A on the exam if and only if she earns 89.5 or more points. That, I think, is necessary and sufficient. It identifies what's necessary and the only thing that's necessary. You may obtain a U.S. passport if and only if you are a U.S. citizen and you complete the application. I'm not sure that's entirely true. I think something else might be required. You got to pay the fee. That is, what about, that's true. Well, this is the thing. It didn't say you may obtain a U.S. passport legally, right? Because people can illegally obtain it in other ways. But you're asking, or you're bringing up the very kinds of issues that will make us, as we're going to do here in a second, turn our attention to conceptual analysis. That is, you have to reason through the reasonableness of what's being asserted as necessary and sufficient. But notice again, these bottom examples, these are not biconditionals. Something has a mind if and only if it is rational. Something has a mind is not a component. It is rational is not a component in the way that you will pass the course and you will attend class are components. Because the it in that first example here is referring to the something. You need the whole thing in order to determine whether it's true or false. Again, general statements, even these complex general statements, are always, without exception, atomic statements. Someone can practice law if and only if he or she passes the bar, and so on. So the reason why we're talking about these 3 kinds of conditions is that in the end, constructing a conceptual analysis requires that you construct a necessary and sufficient condition. Where at each step you're asking yourself, is what I say necessary to be the case? And you're not done until you've identified everything that's necessary. So let's just pick out a couple here. What I want you to do is to tell me what kind of condition is being asserted and whether it's true or false. What about number 1? I can increase the size of that a bit. Number 1, something has a truth value if it is a declarative sentence. What kind of condition is being asserted there?
Sufficient.
I've got 4 people saying that. What kind of condition is being asserted there? Number 1.
Sufficient.
Why?
They're using only if.
No.
You're using the if. I meant like not the phrase. They're using just the.
No, that's a general statement.
That is absolutely a general statement. The question is, how do you know that number 1 is expressing a sufficient condition? And the answer is close to what you said, but you use the word only in there, and the word isn't only in there. So the reason why you know that number 1 is expressing a sufficient condition is because of this. Connective. If is in the middle. What type of statement is being asserted at number 1?
General.
It's a general statement. Is it true or is it false?
Yes.
It's true.
That's true, sorry. That's true.
And why is it true?
Because all declarative sentences do.
Something has a truth value if it's a declarative sentence does not mean the same thing as what you just said. What this says is that it's sufficient. Not that all of them have it. That is, something has a truth value if it's a declarative sentence. And if something has a truth value, it's good enough it's a declarative sentence. Not that it's necessary. What about number 2? Which I'll highlight here. Something has a truth value only if it's a declarative sentence. What kind of condition is being asserted here?
Necessary.
It's a necessary condition. How do you know it?
Only if.
Yes, it's the connective only if. What type of statement is being asserted in number 2? General statement, exactly, not a conditional. Now, is it true or is it false? Why?
Because it's not necessary for it to be a declarative sentence.
Perfect. That's exactly what I want you to say. Don't say, well, because it ain't. You know, that's doesn't tell me anything. In the vocabulary that you're learning today, you know that what's being expressed at number 2 is a necessary condition. And in order for a necessary condition to be true, it must be the case, whatever is being asserted here. And in this case, must it be the case that in order for something to have a truth value that it be a declarative sentence? No. Why? Statements have truth values as well. Beliefs have truth values as well. So it's not necessary. And notice that you're not just regurgitating the definition, you're applying your critical reasoning skills here in order to evaluate the reasonableness of what in this case is being asserted as necessary. Welcome to philosophy. Yes.
So number 1, when I said that all declarative sentences have truth values, that's not it's not equivalent?
It works out to be equivalent, but what the better answer is, something has a truth value if it's a declarative sentence is true, is because it's sufficient.
Yeah.
Not that, as a matter of fact, all declarative
just
sentences have
jumping
truth. It's right, that it's sufficient. What about number 3? Someone lives in California if she lives in Los Angeles. What kind of condition is being asserted there?
Conditional. Sufficient.
It's a sufficient condition. What type of statement is being asserted in number 3? It's a general statement. Is it true or is it false? It's true. That is, it's not necessary, it's sufficient. What about number 4? Someone lives in Los Angeles if she lives in California. What kind of condition is being asserted? Sufficient. It's a general statement. Is it true or is it false? Why?
Because you don't have to live in, just because you live in California doesn't necessarily mean it's Los Angeles.
Well, that's true. But in terms of sufficient or necessary, tell me exactly what's wrong with this.
Living in California is not sufficient to say that someone lives in Los Angeles.
Exactly right. What about number 5? This is easier to see. Someone lives in California only if she lives in Los Angeles. What kind of condition is being asserted here? Necessary. Is it true or is it false?
It's false.
Why? Use the vocabulary.
It's not necessary for you to live in Los Angeles.
Exactly right. All right, we getting this? I'll take a look at a couple other examples here. What about number 14? Someone is a medical doctor if she has earned an MD. What kind of condition is being asserted here?
Sufficient.
Sufficient. Is it true or is it false?
It's true.
That is, it's good enough. Someone is a medical doctor only if he has earned an MD. What kind of condition is being asserted here?
Necessary.
Is it true or is it false?
It's true.
It's true. What about the final one here? Which I hope I can hide. That little thing. There we go. Someone is a medical doctor if and only if she has earned an MD. What kind of condition is being asserted there? And sufficient. Is it true or is it false?
It's true.
It's true. Notice that when the necessary and sufficient condition is true, as in the case in 16, the necessary condition is going to be true, that is number 15, and the sufficient condition is going to be true. Even though you can express a necessary and sufficient condition with anything, doesn't make it true. But if the necessary and sufficient condition is true, the necessary condition is going to be true, and the sufficient condition is going to be true, and that shouldn't be surprising because necessary and sufficient captures what's asserted in both of them. Now take a look here at conceptual analyses. There are many reasons why we use conceptual analyses in philosophy. One of them is when we're trying to answer a metaphysical question about the nature of something. Like what's necessary and sufficient in order for something to be a person, or in our class, what's necessary and sufficient in order for something to be a genuine science? What's necessary and sufficient in order for something to be a pseudoscience? What's necessary and sufficient in order for something to be a hypothesis or scientific theory or a law or an adequate explanation? Right? There are all kinds of occasions when we do that. In logic or generally in arguing, using conceptual analysis is a good way of figuring out, in order to defend your claim, to show that your claim is true, for you to identify what's necessary for you to show in order for you to do that. That is in picking out what ends up being the first premise of your argument. But here are some examples of questions that we ask when we end up needing a conceptual analysis. What conditions must be met for blank to be true? What conditions must be assumed, or what must be assumed to prove that blank is true? As in the case of the argument I was just talking about. What conditions must be met for something to be a blank? Well, answering these kinds of questions means that we're doing metaphysics. Metaphysics doesn't have anything to do with anything spooky or supernatural. It has to do with questions about the nature of being, of reality. So when we ask someone to construct a conceptual analysis, we're asking them to do some metaphysics. We're not asking for a definition of something. We're asking what's necessary and sufficient in order for something to be a thing of a certain sort. And the form of a conceptual analysis looks like this. And the vocabulary doesn't matter a great deal, but I'll just tell you that a conceptual analysis, being an analysis, has two parts. One part's called the analysandum, and the other part's called the analysans. The analysandum is that concept or whatever that you're analyzing. The analysans are all of those necessary conditions where you've broken down the analysandum into all of the necessary conditions that are jointly sufficient. Notice that what we have here is in the form of a single statement. This isn't an argument. You're not making a claim and giving reasons for why the claim is true. You're reasoning at the level of a single statement here. But what you're asking yourself, whatever the concept that you're analyzing is what's necessary and what are all of the things that are necessary in order for whatever it is that you're doing. You're not done until you've identified every single thing that's necessary so that they're jointly sufficient. The example that we'll use isn't something that we're particularly interested in, namely bachelor. But here's how we'll phrase it. Something is a bachelor if and only if 1, 2, 3, and so on. So we're trying to identify everything that's necessary in order for something to be a bachelor, such that those conditions will be jointly sufficient. That is good enough. So we're not opening up a dictionary and looking at the definition of the word bachelor. We're doing metaphysics. We're reasoning through this. And the reason why this is reasoning is because at every step, when you identify something that you say is necessary, you have to test it. Can you come up with a counterexample to the necessity of something you're saying is necessary? If you can, then it ain't necessary. And if it's not sufficient, you're going to have to identify another condition and so on. So if we take a look at the example that we have in the text, something is a bachelor if and only if what? Well, surely it's necessary that it be human. So the question is it necessary? Well, if it's possible for something to be a bachelor and not be human, then it wouldn't be necessary. So it is human necessary to be in a bachelor? I ask you, class. Yes. Is it sufficient? And the reason why it's not sufficient is because there are lots of things that are humans that are not bachelors. So we've identified one necessary condition, but we're not done. So we go on. All right, so what else is necessary? Number 2, it is male. All right, is there anything in the universe that is a bachelor that's not male? I ask you, class.
Oh, no. Sorry.
Yeah, pay attention to the order, because these are the kinds of questions that you have to ask yourself. That is, if you can identify anything in the world that is, in this case, the concept we're analyzing, a bachelor, but is not a male, then being male would not be necessary. So, can you? No. So it is necessary. The question now is 1 and 2 sufficient? That is everything that's both human and male a bachelor? No. So, we got to move on. What about number 3? It is unmarried. So, we've got human, male, and unmarried. So, the question is it necessary? Is there anything that's a bachelor that is not unmarried? No. I mean, you may have married guys behave as if they're bachelors, but strictly speaking, they're not bachelors. You can't be a bachelor unless you're unmarried. Agreed? It's necessary. So the question now is it sufficient? But not just it by itself. We've got 1, 2, and 3. So is there anything in the universe that's human, male, and unmarried that is not a bachelor?
Yes.
If so, then we're not done. We've got to move on. If so, then we're done. So what? In fact, give me an example of something that's human, male, and unmarried that is not a bachelor.
Children.
Children. So little boys, your 2-year-old nephew and whatnot. We need a condition that excludes those counterexamples.
Maybe people who are still legally able but are being like held hostage or something, who've been held hostage all their life.
That's an odd condition.
So it's like they have to be autonomous as well as legally able.
Maybe I'll add that, but it's not just we want to exclude the little boys, because we don't want to say that they're bachelors.
Yeah.
Besides people being held hostage, I'm thinking priests, for instance, we need a condition that excludes them because they're not legally able to marry. And in the end, I'm not really all that concerned about the concept of bachelor, but I want you to see how this works. So we need a couple of other conditions. That is, 2 guys in a committed monogamous relationship wouldn't necessarily be bachelors, right? So we can exclude those kinds of examples. We put all this together, we end up with something like this. Something is a bachelor if and only if it is human, it is male, it is unmarried, it is legally able to marry, it is not a priest or someone who cannot marry for religious reasons, and it is not a gay man who is currently in a committed relationship with another man. For the sake of argument, let's say that that's good enough, that this is a successful conceptual analysis. Notice that at every single step in the process, you have to ask yourself, you have to reason through this. Is it necessary? So you're looking for a counterexample to the necessity of what you say is necessary. And then, is it sufficient? You're looking for a counterexample to the sufficiency of what you say is sufficient. If your analysis admits of counterexamples, it is not successful. I'll be trying to poke holes in yours, you'll be trying to poke holes in one another's. The bottom line is you're not just opening up a dictionary and giving me a definition for something. You're doing philosophy, you're doing metaphysics, you're employing critical thinking skills here in order to identify what's necessary and sufficient. So, as I say here in the text, there are 4 conditions that bear upon whether a conceptual analysis is successful. And these 2 that are here at the bottom and 4 are really, really important. If you can identify a counterexample to something that someone says is necessary, then it is not a successful conceptual analysis. If what they say is jointly sufficient is not jointly sufficient, then you can undermine their analysis. So let's take a look at a few and apply what I'm talking about here. What about number 1? You are a student if and only if you are enrolled at Harvard University. First, what kind of conditions being asserted here? What type of statements being asserted here at number 1?
Conditional.
No. Why isn't it a conditional?
It's a general statement.
Why it's not a general statement either?
But you is specific.
Yes, you is referring to you, right? So go back to my question, what kind of statements being asserted in number 1? Yes, it's a biconditional statement. Biconditional statements are truth functional compound statements. So we've asserted that it's a necessary and sufficient condition. It's a biconditional. Is this a reasonable conceptual analysis? No. What's wrong with what's being asserted at number 1? Use the vocabulary.
Sufficient that you go to Harvard University in order to be a student.
It's not necessary that you be enrolled at Harvard, and it's not sufficient, so it's doubly wrong. What about number 5? Something is a chair if and only if it has 4 legs and it can be sat in or What kind of conditions being asserted at number 5?
Necessary.
And let me ask it again. Class, what kind of condition is being asserted at number 5?
Necessary and sufficient.
Yes, right, because it's if and only if. What type of statement's being asserted at number 5? It's a complex general statement, yes. All right. What about the analysis here? Is this a successful conceptual analysis of the concept of chair?
No,
Why? What's wrong with it?
I could sit on this table.
Use
Oh, yeah, the vocabulary.
the vocabulary.
not
Deal with,
sufficient.
we've got two conditions here.
Those two
You've got either
conditions.
necessary or sufficient. So tell me, in terms of that, James?
Those two conditions aren't sufficient for something to be a chair.
That's something we could say, I suppose, but I think it'd be better if we attack the necessity of them. What's wrong with the necessity of number 1?
Oh, that's true, there are beanbag chairs. Yeah, for example, a beanbag chair doesn't have one.
That is, this asserts that it's necessary in order for something to be a chair that it have 4 legs. You've got chairs in this classroom that did not have 4 legs. Beanbag chairs are chairs, but they did not have 4 legs. So you're attacking the necessity, not just the joint sufficiency. What's wrong with the second condition here? It has to be sat in or on.
But it's not necessary for something to have the ability to be sat in or for it to be a chair.
Not that we can sit on other things, it's just that there are some things that would be chairs that wouldn't be chairs if that were the case. Like if I were to take a chair and tack it up to the ceiling. Well, you can't sit in or on it. A little miniature chair in some little girl's dollhouse wouldn't be a chair because you can't sit in or on it, right? So we're attacking the necessity of each of those conditions. You with me? All right. What about, so like, these came from homework exercises from students over the years, by the way. So I didn't just make these up. Number 6, someone is an NBA basketball player if and only if she or he plays basketball. 2, she or he attended college. And 3, she or he makes, let me scroll over here, earns at least $1 million a year from playing basketball. Is this a successful conceptual analysis, I ask you, class?
It's pretty close, though.
It is?
Yeah, it is, because there is the 1-year rule, but some people go overseas instead of going to college, and there is a minimum salary that's close to a minimum.
And a minute? Are you out of your mind?
The minimum salary in the NBA, I think, is like $500,000 or something.
There's a big difference between 500
Well,
$500,000.
okay, all right.
If I owe you $1 million, you're not gonna settle for $500,000.
Is there anything else that's wrong with this? Can females be members
Also,
of
it didn't mention that you're playing in the NBA. You could be earning $1 million playing in the Spanish league or something.
It says it's someone in the NBA.
Yeah,
Someone is an NBA basketball
Someone
player.
is an NBA basketball
Only if
player.
they play basketball and earn money for playing basketball. It doesn't say that they're earning that money playing basketball in the NBA, though. You haven't specified.
Someone is an NBA basketball player if and only if.
Yeah. They have to be in the National Basketball Association also.
Then we could attack that as being necessary. That's not
Yeah.
included.
There's
So
not a
what's being
condition.
asserted here isn't sufficient. Again, I'm just trying to get you to use vocabulary. All right. This is a good one. Ah, shit, I'm keeping you late. Let's do this last one, then I'll let you out of here. Something is a computer if and only if 1, it has a hard drive, 2, it has Windows, 3, it has an internet network connection, and 4, it can store, retrieve, and process data. Is this a successful conceptual analysis? What's wrong with it?
A lot of those conditions are not necessary.
Yeah. Does it have to have a hard drive?
No.
I mean, not really. I mean, you can run it from a flash drive. It has
it has to have a
Windows.
storage device.
It has a storage
Yeah.
device. That much is true. What about Windows? Is that necessary?
I
All right, you get the idea.
Mine.
I have put up, I won't read it to you because I'll keep you here an extra minute. I put up a 1-minute argument question today. I've given you a list of some possibilities where I want you to do the conceptual analysis about a concept that's related to the class. Once you post your reply, you're then free to post an evaluation of someone else's. All right, and we'll begin next class with that on Tuesday. Then we're going to shift our attention to arguments. All right, have a good weekend.